It's a great pleasure to welcome Professor Gérard Biau at the DATAIA seminar. Gérard is professor in the Sorbonne University, that used to be Paris 6, if I'm right, and is interested in statistical learning and very heavy on the theoretical aspects. I remember the works he's done about about the random forests that were so impressive, and is now the director of the Sorbonne Center for Artificial Intelligence, and he was also president of the French Statistical Society. And today, we are lucky that he will speak about his recent works about the ordinary differential equations and recursive neural network. Welcome.
Thank you very much, Michel. So thank you very much, Frédéric, Michel, Frédéric, for inviting me at this seminar. So it's a great pleasure to talk about the connection between recurrent neural network, RNN, and neural ODE for ordinary differential equations. So it's a joint work with Adeline Fermagnan. So Adeline was a PhD student of mine. She's now at the École des Mines as a postdoc. Pierre Marion is a student from Le Corps des Mines and is right now a PhD student of mine and Jean-Philippe Vert at Sorbonne University. And Jean-Philippe is a Google senior researcher at Google Brain in Paris. So that's the roadmap of today. First, I will try to provide you with some insights regarding the connections between this recurrent neural networks and the so-called neural ordinary differential equation. I will try to make clear the connection between neural networks and differential equations in this context. Then we will discuss more theoretical tools, the way some type of Taylor expansions play a key role in understanding this neural ODE. Also, a very important tool of stochastic analysis, which is called the signature of path. And we will see the connection between neural ODE and the signatures. And finally, as a reward, we will get generalization and regularization bounds on the RNN that we are targeting. So let's start with the beginning, and so that will be a talk about statistical learning. So for a lot of people, the supervised learning problem, the classification problem, is about guessing if you have a dog or a cat or a human face or whatever. And of course, what we will be interested in this talk is about the mathematics which are behind the methods, and about the guarantees that we can have in order to guess the good probabilities of having a dog or a cat or whatever. So we'll be more on the mathematical aspects of the problem. So let me first recall you the way we see the supervised learning problem, and more particularly the classification, the binary classification problem. So the general goal is to understand the connection, the relationship between two variables, one input x and one output y, and both will be random. And for simplicity in this presentation, I will assume that y is binary, so a dog versus a cat. But everything I'm going to say, of course, can be easily extended to the multi-level classification problem or even to the regression problem. I will come back on this a little bit later. So, of course, x, y, they have a distribution. This distribution is unknown, and what we get is data, and this data, they are assumed to be RID, and they have all the same distribution as the pair x, y. So in machine learning, we have a model that's a parametric model, and we just take an input, x, and it outputs a number, m theta of x, and this is using this number that we are going to predict whether we have a 1 or a 0. So if the output is positive, we'll say, well, that's fine, we have a 1, we have a dog. And if the output is -1, then we'll say, okay, fine, we'll have a cat. And of course, we have to measure the quality of the prediction, and this will be done using a loss function. So a loss function is just something which takes as input what we see, 1 or a +1, and we compare this with the output of the model, m theta. So, for example, we may decide that we make a mistake if y is 1 and theta is negative, or conversely, if y is -1 and theta is positive. But of course, we can smooth everything with some more smooth or more elegant function. But the idea is that we can measure the difference between what we predict and what we see. And once we have all this material with us, we can define, well, the optimal parameters. So we call it theta star. So theta star is the best parameter in the model that fits the distribution between x and y with respect to the loss L. And of course, this parameter is unknown since it depends on the unknown distribution of x and y. And so we just replace it by an empirical quantity. So that's just the expectation based on the data, and it's called the empirical risk. It's R hat n. And we have a parameter that we are going to use. This is the best parameter in the model that we can use for next predictions. Okay, so that's the general framework of statistical learning. And of course, then everything depends on the type of data you are using or the type of model you are implementing. And in this talk, we will use very particular type of data. This data, they will have a temporal flavor. So the type of applications we are after is typically time series prediction. So one data is a temporal data. It's a time series. And we assume that we have n time series like this, but one data is a time series. And what we are interested in is predicting, for example, if it's a +1, is it going to increase or to decrease, for example. And here you see that it's a univariate time series. And in many applications, and actually in more and more applications, we have multivariate time series. It means that one x has an output not in R, it's not a univariate time series, it's a multivariate time series. So each observation just makes evolving over time D processes, for example. That's typically the case in sensor data or in many different applications. Of course, time may be embedded in a more subtle way. Just look at this data set. That's a data set from Google. It's called Quick Draw data set. It's a data set where we are, I think, 50 million data and approximately 300 labels. And people have been asked to make some drawings. So you'll see some with more or less success, mushrooms, keyboard, trumpet, whatever. But you see that each observation here is, in fact, a two-dimensional temporal process, but the way it is embedded here, it's in a parametric way. It's a parameterized curve. But of course, if you look at the parrot, you have an X process and a Y process. So it's a two-dimensional time series, and it is written here in an implicit form. But that's a temporal process. And of course, you immediately see that we can have applications for recognition of characters, handwritings, or whatever. And of course, as I said before, one of the main applications of this framework is text translation. And this time, we do not want to predict whether we have a 1, -1, or a number, but we want to predict, of course, something more involved. And I won't discuss this today, but the type of bounds that I'm going to get for the classification problem are easily transposable to this framework. So, in fact, the common features of these examples is that the predictor, I mean, the x, is a path. It means that it's a function from 0, 1 to R to the D, and I insist on the fact that it can be a multivariate process. And that's very important because in many applications of time series, I mean, people are more or less stacked when D is large. And here, as we will see with the methods that we are going to develop today, I mean, D is not an issue. So of course, in practice, you never see the whole process. What you have is that you have the measures of X on a regular mesh, let's say J over T. So capital T is just the number of times you measure the process between 0 and 1. So what you see is an observation here, X, so X bold, and it just corresponds to the measurement of the continuous process over T times, which are well specified. And we assume here that, so each coordinate is capital X measured at J over T. So that will be the general framework of my talk. We will assume that each time series, so each data, is a discretization of a continuous process at regular point, at a regular mesh, and I will assume that the underlying path is of bounded variation, so it's an assumption of regularity, and so I will suppose that the total variation is bounded by some capital L, and that's it. Of course, it's an assumption, and we can discuss it. I mean, it says that the curve, the measurement of the curves are the byproduct of something which is continuous. So, but it's a framework which is, to my point of view, totally acceptable. Okay, so that's for the type of observation that I'm going to look at in this talk. Next, the model, and as put forward in my title, we'll discuss today recurrent neural networks. So it means that we just have a specific choice for the model. So this model, they take as input this discretized time series, and the way they work is quite easy. They work with a sequence of hidden states. So as we have seen, each observation is measured on t time points, and so we have capital T, the same number of hidden states, and the way we pass on the curve from one state hj to the other state hj plus 1 is just by adding to hj, so the hidden state at time t, we had a function f theta of the hidden state at time t augmented with the observation that we effectively measured on the process at time j plus 1, right? So it's very easy way to model the evolution of the process over time. We just say that we have a hidden mechanism that passes from time t to t plus 1, and so we jump from 1 to 2 to 3 until capital T. And this hidden process, the way it is built, is using the observations that we see effectively on the curve. And of course, at the end of the curve, we have h capital T, which is there, and we assume that the output of the model is just W, which is just a matrix, right? Something which is linear, applied to the last time instant of the process. So of course, different forms for f theta, I didn't specify for now, the function f theta, lead to different types of recurrent neural networks. So this mechanism is called RNN, a recurrent neural network. And the typical network of that I will be discussed today is the so-called feed-forward RNN. So a feed-forward RNN just means that this function here, f theta, has the following form. It's quite easy. Sigma is a smooth activation function, so typically logistic or hyperbolic. And the way we combine the hidden state and what we really see at time t over the process is just linear in h, in x, plus an offset b. So u is a matrix, v is a matrix, and b is an offset. And you see, we evolve over the curves with this parameter u and v and b. And of course, it's a sort of neural network. It's a deep neural network in the sense that, well, we have capital T layers, but the parameters of the network, u, v, and b, they do not evolve over time. And they stay fixed one forever. And so it's called the feed-forward neural network, but there are other models, GRU, LSTM, etc., that also fall in this model, and I will discuss this a little bit later in my presentation. Right? So the unknown parameter in this business is theta, so u, v, b, and eventually w, the last layer, the output. And the way it sometimes pictures is like this. So you see, you have h1, h2. So that's one observation, one curve, and we pass from h1 to h2 by using this mechanism there. And at the end of the curve, at time capital T, well, we have the m theta of x, and which make the decision: is this curve a dog, or I don't know, a dog or a cat, or what you are interested in. And of course, what you immediately see is that, well, this looks like a discretized differential equation, right? Ordinary differential equation. That's the Picard iteration of a differential equation. And of course, what we want to do in this presentation is to make this connection clear. And I will show you how we can make this connection clear. So the flight plan of today is to leverage the theory of ordinary differential equation and CDE. So CDE means control differential equations to analyze this recurrent neural network. So the objective is to get bounds, performance bound on these neural networks using the ordinary differential equations point of view. And the general idea can be summarized as follows. We have this discrete RNN, so that's traditional RNN. We are going to see it as an ordinary differential equation, or more precisely as a discretized version of ODE, and in fact as a CDE, a control differential equation, which is something which is a little bit more comfortable in this in the analysis. And at the end, we will see that, in fact, with this point of view, the output of the network is something which is living in a reproducing kernel Hilbert space. It means that it's something which is linear, in fact. It's linear in a particular feature of the process, which is called the signature of the process. And so I think it's very interesting because it shows you that this business, which looks very complicated at the beginning, is in fact something which is linear in a good space. And this shows you that, in fact, this is a linear problem. And so we can then immediately use the very rich theory of reproducing kernel Hilbert spaces, for example, to get bounds, generalization bounds on the RNN, or even use the structure of the RKHS, which has a particular norm, in order to have a guarantee for stability in these networks. And that's typically useful for the so-called adversarial attacks framework. I will come back on this at the end of my presentation. So before we pass from the discrete to the continuous time, maybe a bit of history where we are today. So there is today a very interesting connection between the deep learning world, the machine learning world, and the world of models, of ordinary differential equations, but more generally the world of dynamical systems. And this neural ODE is a little bit the point where everything mixes. And the story is quite recent, in fact. A traditional neural network, I mean, a feed-forward neural network is something where you pass from one state to another by just composing state with f theta. So here I put f theta j, and because for traditional network, feed-forward network, the parameter changes at each layer. And in 5 years ago, there was a very interesting paper by he and his collaborators, and they observed that by adding to a traditional network a so-called skip connection, residual term, hj, then, the predictions are better, it's more stable, the gradients, they don't vanish, etc. So it became the standard. And of course, this small improvement is in fact a deep improvement, in the sense that if you just normalize by 1 over t, and this was observed 2 years ago in a very good paper at NeurIPS. This was, I think, awarded the best paper at NeurIPS 3 years ago. And the authors, Chen and collaborators, just observed that, in fact, these residual neural networks, they were just the discretized version of a continuous differential equation. And so that was the beginning of this neural ODE story, with very interesting applications. So the general idea is now a neural network, a deep neural network, is seen as, a discretized version of something which is continuous. And of course, it's interesting to have the continuous framework at hand. It's interesting because it's much more comfortable, of course. But also, it has very interesting application, in the sense that now you can use the theory of ODE to propose new architectures. You can use the rich theory of ODE to propose new optimization procedures. And also you can use the very rich theory of ODE to analyze these networks, which are complicated to understand. So I think it's a very interesting mixtures of both point of view, the point of view of models with differential equations, and the point of view of machine learning with the data. And you can have a look at this paper, and you will see that they mix both point of view, and they propose very interesting point of views. So in summary, just to see where we are for now, we have on the left the discrete RNN, the traditional RNN. So we have seen that we pass from, so that's one data, and one data is built like this with this mechanism of hidden state. And at the end, the decision is just taking a linear matrix of the last state. And the way we are going to see it is as well, continuous, using a continuous point of view. So this is going to become, as you imagine, dHt is f theta of ht xt. But of course, we have to give a precise meaning to this quantity. That's informal. And the decision will just be w of h1, the last state of my differential equation. And again, the unknown parameter stays the same. It's what is unknown in this story is u, v, b, and w, and that's the parameter of my neural network. And we assume that we have n data like this, and we just feed by minimizing some error the best parameter theta. Okay, so central to my presentation is the notion of kernel. So I guess many of you already know what is a kernel, so I will be very brief. So a kernel is a positive definite function k, which is acting on the purse, the space. And a positive definite just means that if you take all the combinations like this, then they stay positive. And there is a theory which tells you that if you have a kernel like this, then you can define an abstract Hilbert space of functions such that, well, first, if you fix one point, then k of dot x is an element of this Hilbert space. So it's a very abstract Hilbert space, and we have no precise description of it. And if you take one function in the Hilbert space, and if you make the scalar product in the Hilbert space with the kernel, then you reproduce the function at the point x. So it's H is called reproducing kernel Hilbert space with reproducing kernel K. Fine. But what is much more interesting for us is that you have a very easy way to craft kernels, in the sense that if you take one data or one point, you send it in a Hilbert space, call it T, and then you make the scalar product between phi of x and phi of x prime, so two data. And so just imagine that, well, you have one-dimensional data, and then you use the square of the coordinates or some polynomial of the coordinates, then it's a kernel. And so you change a little bit the scalar product. That's the idea. And of course, you hope that in the new space, with this new scalar product, then the problem will be linear. And what is fine is that in this case, when you have an easy kernel like this, then you can totally describe, in fact, the reproducing kernel Hilbert space associated with this kernel. And it's just the linear functions of the data transformed by this feature map x, phi of x. So if you make the comparison with the traditional linear model, well, the linear model uses the traditional scalar product, and here you just change the scalar product. But then everything is the same as the linear model that you all know. And of course, then what you do is that instead of using a linear model in the original space, you use a linear model in the RKHS. So you just minimize the empirical sum over the linear functions in the transformed space, or in a ball of this space. And the theorem tells you that exactly as you have closed form solutions for the traditional linear regressions, you have closed form when you are performing regression in this RKHS with the scalar product. And the solution, they live in a finite dimensional subspace, and we have efficient algorithms to compute the solutions. And of course, this is at the origin of kernel-ridge regression, support vector machines, etc. Right? So that's the general, very brief pictures of the kernel methods. But we will see that this RNN, they allow us to define an adapted RKHS, which makes everything linear. So let's be now a little bit more precise about the way we make these networks continuous. So now, how do we pass from a discrete RNN to an ODE? Well, that's just a very easy application of the Picard-Linhoff theorem. So assume that the function f is Lipschitz. So I skip the theta because everything I'm going to tell you now is independent of the fact that you have a theta or not. So assume that f is Lipschitz in h and x, and we'll see that for for the feed-forward networks, this is the case. So first, there exists unique solutions of the ODE, so it's fine. I mean, the problem is well defined. So if you look at the ODE associated to the network, then it has one unique solution. And moreover, if you look at the discretized version of this solution, you recover the points that you, or the hidden points that you have measured on the network. So up to a constant 1/t, so that's fine. The problem is well defined. We can safely pass from the discrete time to the continuous time. That's essentially what this proposition says. And we see that we lose a 1/t factor, and this factor is just due to the fact that we pass from discrete to continuous time. And we will see that we will find these 1/t factors everywhere in the bounds, also in the bounds at the end of my presentation. So that's the first step. The second step is to pass from an ODE to a controlled differential equation, still under the assumption that f, so the main function of my network, is Lipschitz in both parameters. Then just by having a small trick, so what we do is that instead of looking at the x, the process we are looking at, we look at x, but with we slightly augment the dimension, and we look at x and t. Then we can prove that there exists a tensor field. So what is a tensor field? It's just a function from R E bar. So E bar is E, the dimension of the space, plus D, the dimension of the problem. So it's something which takes as input a vector and which outputs a matrix. So it's called a tensor field, whatever, it's a function. And if you look at the solution which exists of the control differential equations, so this is this differential equation here. So what is a control differential equation? If you are not familiar with this notation, dx bar t, just think as if it were x prime of t dt. If x is differentiable, then it's just x prime of t dt. Otherwise, it's the so-called Riemann-Stieltjes integral, but whatever. It's x prime t dt. So if we look at the solution of this control differential equations, also again, it's with dx bar t. So we have slightly augmented the dimension of the process, and also we have slightly augmented the dimension of h. Then the first coordinate of this equation are in fact the solution of my ordinary differential equation, right? So it's very interesting because it shows you that it's a much more convenient way of writing the problem, in the sense that now it's linear in the x at the cost of slightly increasing the dimension. And of course, if you don't like this notation, just take the integral notation. It means that you pass from ht to ht plus 1 just by integrating like this. But it's the same. And so again, we have the discrete version, the continuous version, and also a way of seeing the continuous version by embedding the problem in a larger space and with a driving process, which is dx. And the first coordinates are, in fact, the solution of the differential equation. So that's the second ingredient of my presentation. So, of course, the classes of functions which satisfy this the constraints are not void. If you take, for example, a feed-forward RNN, so if you assume that the sigmoid is Lipschitz continuous, which is the case for traditional activation functions, then of course the function f theta is Lipschitz. It's a one-line exercise proof, one-line exercise. Same thing, it's Lipschitz in the second variable, so it's fine. The assumption for satisfied. So they are not very heavy assumptions. So it means that, again, for these feed-forward neural networks, if you take E bar, so again, you look at the solution in a slightly augmented space, and you can explicitly have the tensor field. So you see that you have here the original f theta, you embed it in a large space, so you take a more complex f theta, right? But it's full of 0, of 1, whatever. Capital M is just here the concatenation of the two matrices. Anyway, if you take this tensor field f theta, then you can prove that the solution of the control differential equation using this tensor field, if you look at the first coordinates, then they are the coordinate, then they correspond to the ordinary differential equations, which itself approximates the measurements of the networks with a precision 1 over capital T. Now, the last ingredient of my presentation is assuming that the function capital F, so the tensor field is smooth, so just meaning that the coordinates are infinitely differentiable, says, which is the case for the feed-forward neural network, then, and that's the most important part of my presentation, if I denote by Fi the columns of this application, if I call H the solution of the CDE, so now I have skipped the theta because these results, they are more general than for neural networks. So I look at the solution of the CDE, then we can prove that, in fact, the solution of the CDE has the following form.
Je suis tout oui.
Sorry, let me see. The solution may be written in this very interesting form. So it's an infinite sum, which looks a little bit at a Taylor expansion. There is a k, so 1 over k factorial. And then for each k, you look at the k-tuples of coordinates. So d is the dimension of the process. And there is this number here. That's a real number. It's called the signature of the process capital X. And there is one coefficient for each k-tuples of the coordinate. I will explain what it is, and it plays a key role. Times, well, something which is complicated. That's a vector, and that's a complicated operation of which starts with h0 with the initial state, and then we compute a vector starting from this h0. So first, we see that it has the flavor of a Taylor expansion. That's a traditional Taylor expansion, and you see that, well, it's local in the sense that the process of bond variation. So in a traditional Taylor expansion, it's true around the point where we are making the linear development. So it's a little bit the same idea. Well, as I said before, there is this so-called differential product. So here you have the precise definition. It's complicated. It's not commutative. It's a Hughley quantity, but that won't play a very important role in the rest of the analysis. It's there. And as I said before, the important coefficient is this one. And here, for each k-tuple of coordinates, A1, AK, you have one coefficient, one real numbers. And so you have an infinite sequence of real numbers like this. And what is interesting here is that you see that we have separated the part which concerns the process on the left and the part which concerns the network or the mechanism on the right. And finally, of course, it's an infinite sum. So there is some radius of convergence. And so this formula, it's true. I mean, the limit is true, provided the tensor field is bounded locally. And what is interesting is that the assumptions of boundedness are okay. We can verify them for typically a feed-forward RNN with a logistic or hyperbolic tangent activation. So this type of formula, this Taylor series formula, they are known in stochastic analysis, but they never try to pass from discrete to continuous time, right? Because of course there is a bound which measures the rest of the series, and that's what we have. That this rest has to be convergent, of course, and that's why we have assumptions. And in stochastic analysis, it never looks that way. And now here, of course, we are interested in passing from discrete to continuous time, and so that's a very, very convenient one. So you see that very slowly, I am showing that the output of my network, it looks more and more linear. And actually, you can verify on a computer that there is that the series is convergent. And so that's for the two activations, single and tangents, and that the error that you commit between the infinite sum, the solution of the differential equation, and when you truncate the series, and you see that, you can effectively see it on simulation. So that works. So that's where we are so far. So remember, m theta, this is the output of my network for one observation x. That is a discrete observation. So we have embedded in a continuous space. And so the output of my network is just W matrix of the output of the process of the differential equation, which is this infinite sum. And so that you see that we have already made some way. We have passed from discrete to the ODE to the CDE. And now what I'm going to show is that in fact this is a scalar product. This business here is a scalar product between two quantities which are living in an adapted space. So that will be my next step. And for this, of course, we have to work out a little bit more this notion of signature, which is the key, of course, to understand what is behind these formulas. 20 minutes? Okay, 20 minutes. So, so if you are not familiar with the signature, I'm going to show you a small movie, a small illustration. So imagine that you have a star like this. So that's a star. It means that it's a way of just, it's a two-dimensional time series, which is parameterized. So you may, of course, describe it by plotting the coordinates. So here you plot the y coordinate, so the points. Yeah? You follow the star, and then you have a y process, and you could do the same with the x coordinate. And so you have the first one drawing. The signature is totally independent of the coordinate. That's something here. That's a sequence of coefficients here, but which is going to fully describe the star. And it doesn't depend on the coordinate, on the x and the y. It's a sequence of coefficients which is going to describe the process, the two-dimensional process associated with my star. And it's interesting because, of course, if you run over the star at different pace, just, for example, running very fast at the beginning and then very slowly at the end, then the y coordinate is going to be totally different. The signature is going to be insensitive to this change. If you take a reparameterization of your process, then it's invariant. Same thing if you make a translation of the star. If you make a translation of the star goes up, the y coordinate is going to change. The signature won't. And in fact, this transformation, the signature, you can prove that up to reparameterizations and up to translations, it fully describes the original process. Of course, the signature is going to be dependent of other transformations. If you rotate the star, then the signature is different. If you crunch the star, then the signature is going to be different. And of course, if you delete whatever, make some transformation on the star, the signature is going different, of course. But it has the very interesting flavor of being independent of the time parameterization. Okay. So now, to be a little bit more formal, let's talk about the signatures. So first, a bit of history. This signature story started in the 50s with the work of Chen on smooth path, on iterated integral of smooth path. Then it was captured by the probability community, and in particular by the rough path community as a tool, and in particular by the team of Terry Lyons at Oxford, and which made a lot of very, very interesting developments on this signature, and they use the signature as a tool. And now you see more and more papers in the machine learning field which are using these signatures as a way to describe a temporal process. If you have a temporal process, a multivariate temporal process, it's a way to have features of a process. And so, of course, it's interesting for handwriting applications, for character recognition, this type of business. And you have more and more papers on it on the web. So formally, that's the way it works. So you have a path from 0, 1 to R to the D, and x1, xd, they are the coordinates. So it's a temporal path. So take one coordinate, a1. So the coefficient here, so it's between 0 and t, so t is time of x, my path, and so I1 for the coordinate number 1, is just the following integral. So again, if you don't like this dx, just think about it as x prime dt. So you integrate between 0 and t, the coordinate number 1, I1. So of course, that's the coordinate at time t minus the coordinate at time 0. But of course, it's between 0 and t, so it's a path again. And so you can play the game again. You can take now a second coordinate, a2, and look at this coefficient there, which is going to be the path pertaining to the first coordinate integrated against the second coordinate, the x2, the xi2. And then play the game. It's very easy to compute. That's what you have. And it's between 0 and t, and it's a path again. And you can play this game forever. You can play this game forever, and for each k-tuple of coordinates, then you have a coefficient, which is just the following iterated integral. Of course, it's non-commutative, and you play. I mean, the coefficients they are. I mean, the coordinates are playing one against each other. So I mean, A1, A2 is not the same as A2, A1. And it's called the k-fold iterated integral of x along A1, AK. And this is the sequence of all these iterated integrals, which are real numbers, which is called the signatures of my path, or my process x. So we start with 1. You do not integrate any coordinate. Then we have the d coordinate. It's a d-dimensional process. Then you play one coordinate, the pairs of coordinates, and then 3 coordinates, 4 coordinates, etc., etc. So you see that, for example, in dimension 3, if you have a 3-dimensional time series, then it's going to be a, going to have a big sequence. But whatever. And of course, this notation is a little bit heavy. So very fast, we use a different notation. We use a so-called tensor notation. So it means that k is 1 for the vectors, 1 coordinate. K is 2 for the matrices, the pairs of coordinate, etc. So it's the k-dimensional tensor space, right? And so with this notation, you see that the signature is a constant, a vector, so the coordinates in dimension 1, and a matrix, the pairs of coordinates, etc., etc. But the way we see it is just a collection of real numbers. We put everything in a big vector. And of course, this big vector of this big sequence is living in the so-called tensor algebra, which is just the sum of the real numbers of the vectors of the matrices, etc. And so let's have a look at an example. It's very easy. If you have a 2-dimensional time series, then you have the first coefficient, which is 1. Then you look at the coordinate. Then you just integrate the 2 coordinates, the first and the second. And then, of course, if you know the process, then that's very easy to compute. Then you look the pairs of coordinates. So you are going to have a matrix, coordinate 1 against 1, 1 over 2, 2 over 1, etc. And then you can do this forever, for 3, 4, 5, etc. Of course, in practice, we will truncate the signature because we cannot work with infinite sequences. So we truncate the tensor at the order m. But already, if we truncate the tensor at the order m, we have a quite big dimensional vector. For example, if you have, let's say, a 3-dimensional time series, and you truncate the signature as order 7, you have already a vector of size more than 300,000. And so it's 3,000. Vector of size 3,000, which is already something, because this will play the role of the feature. So it means that if you then use machine learning behind, then you will have a problem in dimension 3,000. And of course, then if you have a process in dimension 6, you truncate at dimension 7, then you have a huge dimensional vectors. But okay. And I will be very brief on this, but the signature has very interesting properties. For example, the first coefficient they are measuring the area under the curve of the process, above the curve. So it's a way of scrambling the process, and looking at more and more refined geometrical characteristics of the process you are interested in. And we can compute it very efficiently. And in fact, we only need to be able to compute linear path, in fact. So if you have a linear path, so a path of this form here, then, well, it's a 2-line exercise to prove that the coefficients of the signatures A1, AK for a linear path are the following form. So it's very easy to compute. And it's very useful because in practice, you always deal with piecewise linear path. You have a discretized time series, then you just smooth it with the process of with a linear bidding, and then the only operation that you need is a concatenation operation, and this is very easily done using an operation which is called the chance identity. So in practice, we can have very fast algorithms in order to compute the signature of a process. So why is it interesting in our case? Well, remember that the signature is a big dimensional sequence which is living in this so-called tensor algebra. Now I look at a smaller space of this tensor algebra. I look at all the series of coefficients which are the norms. If you look at the norms, they are the sum of the square is finite. It's a finite series. So here, this norm, you shouldn't be afraid of this. This is just the norm of the vectors plus the norm of the matrix, a Euclidean norm, plus etc. So it's a subspace of my tensor space. And actually, you can prove that it's a Hilbert space with a very natural scalar product, which is the sum, the infinite sum of the scalar products for the real numbers plus the scalar products for the matrices, etc. Very easily. And the signature, in fact, the key element is that the signatures, we can prove that it lives in this Hilbert space, provided we slightly renormalize it with a k factorial, which is nothing. So that's my proposition there. If you take, well, the augmented process, now I'm coming back to the beginning of my talk, then we can prove that the norm of the signature in this subspace of square summable sequences, then the norm is bounded. So it means that the signature of my process is living in this Hilbert space. And so now that's the beginning of everything, because we immediately have a kernel. As I said in the beginning of my presentation, you can take 2 time series. You look at the scalar product of the signatures of both time series, the scalar product that we have just defined before, just making this infinite, just taking this infinite sum. And then, of course, if you have a kernel, then as we have seen, we have a linear space using this kernel, which is the space of linear functions on the signature. And so now back to what we have seen at the beginning of the talk. That's the output of my network. We have W, linear matrix of this infinite sum. Well, if we make W enter the sum and call alpha theta this parameter here, so we immediately see that what we have, in fact, is a scalar product between the signature of the process and something which is living in the space T. And so it's an element of the Hilbert space. So it's nothing but a linear operation in this Hilbert space. So we are here, and we see that we pass from this discrete RNN to the fact that the output of the network is in fact a linear function of the signature. So the take-home message is that the output of the RNN can be interpreted as an element of a particular RKHS. And I proved this, or I gave you guarantees for RNN, but this is also true for GRU on LSTM. There are other types of RNN. And of course, it's very interesting because now, I mean, a world is opening, because we have now the world of linear RKHS, and we have a lot of understanding of these spaces. So it facilitates the analysis of generalization by leveraging kernel methods. And this can also provide new insight on regularization strategies to make the RNN more robust using the norm in the RKHS. Right? Fine? Oui? OK.
Attends, Gérard, prends le temps que tu veux, c'est bon, hein. Va jusqu'au bout du message.
OK, merci, merci beaucoup. Donc j'en ai pour 10 minutes, maxi. 10 minutes maximum. So now let's see how we can reward what we have done. So back to the binary classification problem. We have the neural network, the predicted class, so nothing has changed. And I use a logistic loss. It's a loss which is a little bit smoother than the hard thresholding loss. And so what we can prove is typically this type of theorem. So assuming that the weight of my neural networks are bounded locally. So why? Because that's just the transposition of the conditions that we have in these Taylor series expansions for the neural networks. So we can prove that this parameter alpha theta, remember that's the parameter of the linear interpretation of the signature. It's living in a ball. So we can prove it. And so once we have this, then we can use the results which are already very well known in the machine learning community regarding kernel methods. And we have results like this, which are not very demanding in terms of math because they are already results for kernel methods. So this typically tells you that the generalization error, it means that xy is the distribution of my process. Theta hat n is the parameter which is filled by empirical risk minimization. So the probability that we make a mistake, that we decide that it's a dog, and a mistake because it's Elon Musk, for example, or whatever, it's smaller than the empirical error, plus a parameter, a term which is measuring the approximation of continuous time of, continuous versus discrete time, plus a term which is accounting for the variance, traditional term, plus a reminder term. So you see that you can have many, many interesting rewards. And if you attack the problem at the originally with the neural network, it's going to be very, very hard to have results like this. But if you pass by this mechanism of continuous interpretation and then linear interpretation, and it's free. As I said before, we can also have similar results for the so-called sequence-to-sequence learning. In that case, it's not a classification problem, it's a regression problem, but it works more or less the same, except that instead of having a 1 or +1 at the end, well, you predict a word at each step of the neural network. I speak French, then it's immediately translated into English or English into French. And but the mechanism is the same, and you may also derive bounds on the generalization bound exactly the same way. Now, why is it interesting for having a regularization and stability strategy? Well, if you take two inputs, I mean two curves, two processes, then you look at the output of the network. So you compare for fixed theta, you compare m theta and m theta x prime. Then using the rewriting of everything as a linear function, then you see that you have this 1/t parameter as usual, and time plus the scalar product between the signature of x, the signature of x prime, computed against alpha of theta. And using Cauchy-Schwarz, this is certainly smaller than this, the norm of alpha theta. So alpha theta, it's the parameter of the linear model, times the difference of the signatures in the Hilbert space T. And of course, we see that if the two data are closed, if the two time series are closed, the two processes are closed at the beginning, then of course, if the discrete data are closed, then so will be, of course, the continuous versions. And of course, the signature is continuous. So also, the difference of the signatures will be closed. So we see that one measures up to this 1/t terms, the stability, I mean, the perturbations of the output of the networks is the norm of this alpha of theta. So the idea then is quite natural. We may say that we may implement recurrent neural network using the natural penalty, which is the penalty of the norm of alpha theta in the space tau. Of course, it's not easy because this alpha theta is hard to compute because you remember it's connected to this product of matrices and it's not commutative, etc. But anyway, we can in easy cases compute it. And let me show you an example. In the case of adversarial attacks, in the robustness of these attacks. So it's a toy task. It's about classifying the rotation direction of two spirals. So we have many spirals like this, and these are the data. So some spirals are going to the right, and some spirals are going to the left, +1, -1. And we want to decide automatically whether they go right or whether they go left. And we see that each spiral, it's a time series. Again, it's a parameterized way of seeing time, but if you deploy the series, and you have an x and a y coordinate over time. And so we use a feed-forward RNN with 32 hidden units, so it means 32 time, with hyperbolic tangent activation. And what we are interested in is in the so-called adversarial example framework. So for this, what we do is that we have a training sample, so we feed the network as usual, and then we have the test sample. And what we do is that we modify the test examples, the curves, we modify up to some parameter epsilon in order to maximize the testing error. We see how does the network resist to a change of distribution in the test observations. And so we just modify the test error in order that they stay within a ball of radius epsilon. And of course, it's called projected gradient descent in the sense that each observation is going to be modified individually up to epsilon in order to fool the neural network. And we see here that what you see, that's epsilon here. So of course, and that's the test error. And when epsilon gets large, of course, the network is totally lost. It has been designed on training data, then you modify the test data. And of course, the performance is deteriorating, and that's normal. But you see that using this penalty stabilizes somehow the network. So there is a good direction. I'm not saying that it does everything, but the idea is there. Using this type of norms, which are the good norms for the networks in this context, makes the job. And so now we can compare the norms, etc. But these norms, they have nothing to do with the Frobenius norm, so we don't know exactly the way it behaves. So, and that will be my conclusion. There is still a lot of work to be done. So the message is that this RNN, they can be framed in the continuous time limit as function in a reproducing kernel Hilbert space. And the key element to obtain this reproducing kernel Hilbert space is the signature. So I think it's interesting to use this tool, which is a tool from stochastic analysis, and to see the importance that it has in the analysis of neural networks there. And for free, it provides generalization guarantees and regularization strategy. That's a little bit in the spirit of the work of Julien Méral for convolutional neural networks, which also shows the connection in a different context, but also the interesting connection between kernel methods and neural networks. And there are, of course, a lot of open questions to leverage this theory, both from a practical side and the theoretical side. Also, maybe that's for a particular type of neural networks. I have studied the case of recurrent neural networks, but we can also analyze the case of residual neural networks. They work different way, but still the signature can play a role in the analysis. And so more generally, I think it's a very exciting domain because it's a moment in time where the machine learning is talking to the world of differential equations. And so I think, well, it's a very exciting moment for math, and there are probably more and more to be done in this field. And I hope I convince you that there is a lot of interesting stuff to be done. Voilà. Thank you very much.
Thanks a lot. Thanks a lot. We're convinced. Thank you very much, Gérard. If you agree, I will start with some questions in the chat. So I see that there is a first question by Frédéric Lefebvre-Naré about the signature. That is, the question is whether it's dynamic time warping invariance.
Sorry, it's not exactly time warping. It looks a little bit as time warping, but it's not exactly time warping.
Okay.
So it's connected. It's a little bit the same spirit, but it's different.
Okay, because I think, okay, so please, I guess that Benoit, you see people raising their hands, right? Or if you want, okay, I see if someone is raising their hands in the chat, please do, or write in the chat so that we can continue. So you see, it seems that the secret of everything is to understand what the notion of signature, right? Because you're using a signature to go in a linear space, and then you leverage kernels.
That's correct. Yeah.
I was wondering whether we have specialists in the audience about the geometrical data analysis. I was wondering if there is an equivalent or a similar notion in the geometric data analysis with the signature. You know, it looks like, okay, the graphics you were showing to see how the signature evolves when you modify the star were very illustrative, and I was trying to understand. So you take the integral. Could you put the definition of the signature, right? Because I think that this is the key point that we need to understand.
That's it. It's there.
Yeah. So the beginning of the story, you see, if you are doing this, right? So actually, it depends not at all of the. So if I'm looking at SI1 on 0 on this, right? It doesn't look like it depends on the time at all. You take the end value minus the start value, right?
That's correct. Oops, je m'entends. So yeah, you take the value at time t. So you integrate between 0 and t.
Yes.
Yeah. So you have the process, and you look, so that I1 is the coordinate of the process, and you look at the difference between the coordinate at time t minus the coordinate I times 0. So it
right.
the difference in time, because you make it between 0 and t.
Yeah. So okay, yes, this is okay. Sorry, and when you are doing with linear things, right? It looks like you have just the product of the
Oui.
just the product for every, say, k-tuple. Yeah. For every k-tuple, you have the difference between the end and the
Absolutely, yeah.
in the beginning.
Now, the question whether there is a connection with some geometrical tools, then we should talk to experts, yeah.
Well, I guess that we have experts in the audience, but okay, perhaps this is a too difficult question to tackle
Maybe
this
Pierre,
online.
there is a
Right. Because it looks also, you see the because people have been looking for decades, for centuries perhaps, of ways to describe shapes. And I was wondering whether there was a relationship between this and that. Okay, so we have the signature, and you're saying we can compute them, especially if we are linear, right?
That's correct. Yeah. And Pierre had a remark, so I don't know if you can you hear?
Ah, Pierre, oui.
Yeah, so the mathematical sense is that if you have xt between 0 and 1, and you take x psi of t, where psi is a surjective, continuous function, surjective and continuous, then the signature is the same.
We can't hear Pierre.
I mean, the signature of x of t is the same as the signature of x of psi of t, where psi is a surjective continuous function. Absolutely. No. Oui.
You integrate from 0.
Yeah.
Like for the 1.
Correct.
Please, Gérard, repeat the question or the remark.
Yeah.
Because we can't hear anything.
Yeah, that's it. Yeah.
Okay, so you have a...
Yeah, absolutely.
Also to apply psi of psi.
Oh, oui, bien sûr. Of course, yeah, exactly. Oui.
So, okay. Oh, Joan says, okay, I saw a comment. Yeah. So Joan was saying, was asking another question, is that
Maybe Johan, you can.
Okay, so I'm sorry, Michel. So Pierre was making a very interesting comment. He was saying that.
Okay, then go on, Gérard.
Sorry, we were discussing with Pierre in the room. So Pierre was, maybe you couldn't listen to him. He was saying that the reparametrization trick in order to have invariance of the signature was something which was very connected to time processes. In fact, that you have the time at the beginning. So it's something which is very special, in fact, for time processes. Well, that was the remark of Pierre, if I am correct. For one-dimensional objects, absolutely. So sorry, Michel, there was another question.
No, that's okay. So let's come back to this remark later on. The question in the chat is, of course, thank you. And then the question is connected to the transformers.
Yeah.
So people are using transformers. That is, perhaps you might want to say a bit of this for people who are not aware of this. Do you think that something can be done? I mean, similar to the signatures, considering the transformers architecture, and particularly whether attention matrices could be closed, could be similar to kernel ideals. So
yeah, I think it's a very, very interesting question, and I have not the answer to this question, but I think it's a very, very important, interesting question. That's a very interesting way. I don't know if it's going to be fruitful or not, but I think it could be a very interesting way to attack the theory of transformers and attention models. Yeah, but I've definitely not the answer to this question. But it's a natural and good question.
Thank you. Is there another question in the audience? So perhaps you might want to, okay, in case that not everyone is very familiar with transformer, you can see, you can explain why this is related, right? So the transformer is the fact that you have the weights, which depends on the previous layers. So in the ideas of the residual networks that you were mentioning as a first step toward the ODEs, right?
That's correct. Yeah, but here you see that in the RNN case, the weights are fixed, and so they don't move from one layer to the other. That of course that's different of what happens with a residual neural network, for example. And so of course when the weights are changing from one layer to another one, then maybe it's going to be, I'm not talking necessarily for transformers, but I'm also maybe talking about traditional feed-forward neural networks. Then analyzing that way these neural networks, you are going to drive the differential equation not by the observation, which is fixed at the beginning of the network, but by a continuous version of the weight. So time does not play exactly the same role for at least for residual neural networks, and I think it's going to be the same for the transformers. Not sure, right? Because here in this RNN, the fact that we have the signature of the process is very natural, because again the process is transformed on the curve. But for residual neural networks, the observation is fixed once and for all at the beginning. So it's going to be the signature of not of the process, but the signature of a continuous version of the weight. And probably this will be the same for transformers. Again, Michel, not sure at all.
Yes, we have to think. I don't know whether Jean is willing to say something more, or if someone has another question.
Fred has a question, I think. Yeah.
Ah, Fred, écris la question.
It's in the room.
No, in fact, he doesn't.
Oui.
Signature continuous, you said.
Yeah. No, I think well, we should go deep into the probability theory papers to have it. I think it's somewhere, but I have no idea.
Some kind of,
Yeah.
For some families of signal or something.
Yes, but of course. Yes.
Could you maybe summarize the question?
Yes, the question was, I said here, so that was the question of Frédéric, which is a good question. I said, where was it here? That the signature is continuous, which is true. And Fred was asking, do you have an idea? It's there, sorry, it's there. So I said here, so you have this 1/t term, which is regarding the discretization of the network. Then the signature is continuous, meaning that if x close to x prime, then this is going to be small. And then, of course, we play on the norm of alpha of theta. And Frédéric was asking the question of whether we had an idea of the modulus of continuity of this of the signature. And it's probably somewhere, but it's not in my head. So I'm sorry. What is true is that it's going to depend on the regularity, of course, of the signature at the beginning. And don't forget that we are assuming that the process has a bounded variation L. So it means that if L is small, it's going to be more severe. If L is large, it's going to be less severe. And so that and also this RNN. It's a little bit counterintuitive here in the sense that it's a little bit like if you look at this equation, you say, well, if you have more data, so 1/t is going to become small, and it seems that it's going to be better. It's a little bit counterintuitive because these RNN, usually they have problems in handling large dependencies. But of course, what is hidden is the fact that we assume that the data, the process are bounded by, in total variation by capital L. So if you have more and more data, and it's connected to your question, of course, if you have more and more data, it means that, there will be more irregular. And so capital L is going to be larger. And so in that case, we will lose something here, probably, yes. But I don't know exactly where and how.
But in that case, we could play with the level of discretization, right?
Oh, absolutely. Oui. Yeah. Yes and no, depending on the applications. Because in some applications, you can play with this level of discretization. In other applications, I mean, it's given by time. Huh? So, I mean, theoretically, we can probably play with it. Practically, not sure.
No, the question is whether you can, so you have the vision of what the data is, right? If you don't have the data online, but if you have all at once.
Exactly.
And then the question is whether you could have, say, something like a multi-fidelity, something like you could have a first approximation of the process with a given discretization and then refine this approximation.
Yeah. Okay, it's another way of thinking the problem, yeah, absolutely. And we can also probably play with the, as they do in the Runge-Kutta method, with 1 over t, play 1 over t power beta, etc. Yeah, sure. Yeah. There is a lot of work to be done. Huh?
Yes, it looks so. So we have a question of Andrea Araldo, saying asking how the truncation of the Taylor expansion is related to the other dimensionality reduction techniques. Whether it's related.
Maybe let me add, because here you said that you can come up with a very large set of features when you compute signature. So now you have a lot of choices you can make. You can truncate at a certain point sooner or later, or you can also play with this discretization step. Or you can also then, a posteriori, once you have maybe long signatures, apply some dimensionality reduction. So in a practical context, how would you choose how to play with these three possibilities when you have a certain problem at hand?
Yeah, I've not. That's a very good remark. I don't know. I'm unable to answer this question, but it's perfectly correct. We have the order of truncation of the signature. By the way, there is something we observe in practice, that the sparsity of the signature, and I think it's a very interesting problem, because what we have is that a lot of coefficients are in fact 0. So it means that the features are sparse. And so for which processes, when, how, I don't know. So we have this first possibility. As you said, we have the possibility of truncation of the series expansion. And of course, they are connected. I don't know how they are connected. And of course, then we have the discretization of the series. And all these parameters, they should play together. And we should run much more involved experiments in order to see which parameters are crucial and which are not. So I'm sorry, I don't have the answer immediately to this question.
Thank you. Having no answer is an answer in some way. There's still work to do. Yes, thank you.
Yes, thanks. Because so as we should go for 1 or 2 questions perhaps, and then free Gérard and the others. Actually, I had the last question along the line of the Andrea's comment, which is the fact that now that you can project every process in the signature space, right?
Oui.
And then the question is, what happens if you do clustering in this space, right? I was wondering whether you should extract something, and what would be the clusters, if they can be intuitive, or if they are, say.
I don't know. Actually, well, the signatures, they are a very natural way of having features for any process which is temporal. So once you have the features, then you can run you can run any algorithm, supervised or unsupervised, and just making some kind of functional data analysis. Right? So it's a natural way of performing functional data.
Yes.
Then of course you can perform unsupervised learning, as you said, and I don't know exactly what will be the clusters, but probably the clusters that you are going to get are connected to the geometrical properties of the processes, and it's not connected to the if you cluster with the Fourier basis or with a wavelet basis, then you will have a particular clustering, but I'm pretty sure that we will get different clustering based on more geometrical properties. But again, this has to be tested and implemented, and I mean, there's a vast field to be explored.
Yeah, so I think so. So I think that now everyone is convinced, and thanks a lot, Gérard, for introducing us to this new field, at least for many of us.
Thank you very much.
Thanks a lot. Bravo. Merci.
Thank you.